My chemical engineering project is about the invention created by Donald Campbell, which was the fluid bed catalytic cracker. Now, I'm pretty sure everybody here knows what catalytic cracking is. It's a process where we convert heavy petroleum fractions into lighter, more usable hydrocarbon products inside a reactor with a catalyst. Now, in industrial processes and in large scale processes, this catalyst is known as zeolite, which is a mixture of aluminum, silica, and oxygen. Now, to understand why we needed Donald Campbell's invention, we have to understand the process of cracking used before his invention, which was the fixed bed catalytic cracking. Now, I shall explain the whole process to you. So here you have a preheater and you have crude oils. So first what happens is the crude oil is fed in and the preheater which is about 425 degrees Celsius to 450 degrees Celsius will heat up the crude oil so that most of the crude oil out here is in its vapor phase. Then the crude oil is fed into a catalyst chamber. In the catalyst chamber, there are beds of zeolite catalysts stacked one on top of the other, and they are fixed. That's why it's called a fixed bed catalytic converter. And the vapors of the crude oil start to get cracked in the presence of a catalyst. And after it's cracked, it would head out and into the fractionating column. Now, if you don't know what a fractionating column is, a fractionating column is a distillation method which helps separate by boiling points and molecular size. So the lighter crude oil fractions are collected as gases on the top, while the heavier oils are collected at the bottom of the fractionating column. Now, gasoline is usually in the middle layer, and that's what we aim to collect in this catalytic cracking. That's why gasoline's thing will be fed from here and into a cooler. Now, the cooler here will condense the gasoline back into a liquid. But the only problem now is it's not pure. The gasoline needs to undergo a process in the stabilizer, and the stabilizer will collect the flue gases or the dissolved gases from the top and pure gasoline from the bottom. And we got our goal, which was gasoline. Now, you might not know the problem with this method right yet. And I will tell you that the problem here actually lies in the catalyst chamber. Now, because the beds of the catalyst are fixed, there is a problem of catalyst exhaustion. Now, you might not know why a catalyst gets exhausted, and I will explain it here. So, this is a picture of enzyme catalyst, but I like how well it explains it, so I'm going to use this picture. So this is your crude oil, right? And it will touch the active sites, and then it'll break down into two products, and that's how a catalyst works. There is an active site that is important. But what happens is we have a formation of a substance we don't want, and it's called coke, and its chemical formula is C2H6. Now, coke kind of starts to get absorbed on the surface of the active site or the catalyst, and it causes a blockage of the active sites so that the crude oil can no longer touch the active sites. And you can see how this reduces the catalytic effects and the performance of the catalyst, because if it can't touch the active site, it can't perform as a catalyst. So what happens is after a while, the the reactor has to shut down so that the catalyst can be regenerated. And once you shut down the reactor, what you have to do is you have to remove these fixed beds one by one. And the fixed beds are giant, and this process takes a long time, and it becomes like a batch process that it's not working all the time with minimum things. And so what happens is once the beds are out, the old catalytic chamber is heated with oxygen because coke is a C2H6 product, which means it can be combusted into CO2 and H2O in the presence of oxygen. And so a new catalytic chamber is put in. So there's two catalytic chambers, an old one and a new one, and they are switched periodically. And so when they are switched, you have to stop the whole reactor and it becomes a batch process. So since this process can take a long time, Donald Campbell thought, is there a way I can make this process quicker? And the answer is, of course, very simple. Otherwise, I wouldn't be doing this project. There is a way, and that way is the fluid bed catalytic cracking. Now, this method is very simple to the fixed bed, except instead of just a catalyst chamber, there is a catalyst chamber and a catalyst regenerator. And this is how we make our process a continuous process. So let's talk about it again. So again, the crude oil goes in from here and the preheater heats it to 425 to 450 degrees Celsius. Then the crude oil in gas phase will go up here and into the cracking chamber, the catalyst chamber. And here, under the beds of catalyst, they'll be cracked. But these beds of catalysts are not fixed, they are fluid. And so the catalyst used can be dropped here. And this is a blower. So it will blow air in, and the catalyst dropped here will go back here to the catalyst regenerator. Now, in the catalyst regenerator, it is combusted with an excess of oxygen and flue gas exits out from here because this is CO2 and H2O. And it exits out from up there. And the catalyst, the new catalyst, the fresh catalyst is dropped back in with this, in this line, and more vapor is cracked here. And so it's a continuous process, it's a cycle. The catalyst drops from here, goes back up here, gets regenerated, and drops back here. So it's a feedback loop. And so again, the crude oil is cracked and heads to a fractionating column, and the heavy oil is collected from the bottom, and the lighter oils are collected from the top. Here, the lighter oil is gasoline, so it's fed through a cooler and then a stabilizer, and you get gasoline out. Now, you can see that in a fluid bed, everything is a continuous process. You don't have to stop it, and it becomes a little more convenient. And that's why this invention was needed. I think it was very smart for Donald Campbell to have a catalyst regenerator as part of the machinery. So now you don't have to stop in the middle and you don't have to worry about coke formation because everything is getting combusted. But it does take more energy than a fixed bed. But you have to think about the cost analysis. Taking out the beds of catalyst from a fixed bed takes a lot of time and it's huge. So it takes a lot of manpower and machinery. That's why a fluid bed was needed. And this is now the new industry standard. Thank you all for listening. In my Notion page, there's more information about what coke is, what is thermal cracking, what is catalytic cracking, what are knocking properties. So if you're more curious about cracking in general, you can visit my Notion page.